Hi everyone. Today's video is on piecewise functions. So what piecewise functions are two different functions pieced together to be a single function. So we have two different functions here, x plus 5 and 2x minus 1, and they are pieced together to be a single function. But each part of that piecewise is restricted on its domain. So the first part only goes up to x equals 3, and the second part starts after x equals 3. So piecewise functions always have this restricted domain to them. So when we are evaluating a piecewise, we have to remember, since that domain is restricted, we have to plug our values in to the appropriate equation. So if we're looking at g of 7, we have to ask ourselves, which equation does that go in? So ask, is 7 less than or equal to 3, or is 7 greater than 3? 7 is greater than 3, so we're going to put it into the bottom equation. So we're going to put 7 into 2x minus 1. And when you solve that, 14 minus 1 is 13. So g of 7 is 13. Let's look at g of 0. 0 is less than 3, so I am less than or equal to 3, that is. So I'm going to put it into the very first function, x plus 5. So 0 plus 5 equals 5. So you just have to choose the appropriate function of that piecewise function. All right, you try the next two, see if you can do those. Okay, so negative 1 is less than or equal to 3. So I'm going to go ahead and use the first equation. So negative 1 plus 5 equals 4. And actually, let's do this one first. If we do g of negative 3 is less than or equal to 3. So we're going to do negative 3 plus 5, which is equal to 2. But go ahead and change this to a positive 3. Which function are you going to use now? You should be using the first function because that's the one that says less than or equal to 3. So I would be using 3 plus 5, which is 8. Okay, so that cutoff, what is the value of that cutoff is important. All right, let's try the next one down here. We have this piecewise function, and we're looking when x is negative 4. Negative 4 is less than negative 2, so I'm going to be plugging it into this equation. So 1 over negative 4 minus 4. What does that equal? Well, negative 4 can reduce with this 2, so I'm going to have negative 2 minus 4, which is negative 6. Okay. Negative 2. Look at my restrictions. The top one is the one that says less than or equal to negative 2. So because it's equal to negative 2, I can use the top one. Must use the top one. So I have 1/2 times negative 2 minus 4. What does that equal? This negative 2 and this 2 reduce, so it's going to reduce to a negative 1. Negative 1 minus 4 is negative 5. Why don't you go and try the next two. Alright, so negative 1, I'm going to be using the second function because negative 1 is greater than negative 2, so 3 minus negative 2 times negative 1, which is going to equal 5. And then 6, which is greater than negative 2, so 3 minus 2 times 6, which is 3 minus 12. 3 minus 12 is 9. Okay. So that's how you evaluate a piecewise function, but now we're going to look at how do you actually graph piecewise functions. How I normally do this is I start with a pencil and I go ahead graphing each of these functions separately. So x minus 4. X minus 4 has a y-intercept at negative 4 and then it increases by 1 each time. So something like this. But I know my function only exists when x is less than 2. 2 is right here. Our function only exists left of that. So I'm just going to go ahead and erase up until 2, when my function exists at 2. Now it also says less than or equal to, so I'm going to fill this in with a dot. And then this function continues to the left. The next function is 3x. So 3x, I'm starting at the origin. I'm going up 3 for every time I go over 1. So up 3 over 1, and then it looks like I'm going off the page. So it's going to be a line that looks something like this. But 3x only exists when x is greater than 2. So looking at this line of 2, it only exists after this point. And it's not equal to, so it's an open dot. And then our function is going to continue on. So I'm going to erase everything else right here. So this is the graph of our piecewise function. Notice that there can be gaps, but you need to make sure which end has an open dot, which end has a closed dot. Okay? So graph each function separately, and then just erase the parts that you don't want. So let's try this one. H of x. Actually, I'll have you try this one. So go ahead and pause the video and try it. Alright, so we're going to go through this. So we're going to have an x-intercept of 7. Oof. So something like that. And then we're going to go up 2 every time we go over 1. So something like that. So that's our first part of our function. And that only exists when x is less than -1. So -1 is right here. It only works when we're less than that. So none of this stuff right there exists. And it is equal to, so there's going to be an open dot at -1. Alright, next we have -x plus 4, so I have an x-intercept of 4. And then I'm going to go down 1 every time I go over 1. So it's going to look something like this. And notice my function only exists when x is greater than -1. So everything to the right, so that means this is no longer there. So it looks like this V shape. And notice this dot can be filled in because it's the same point, same y value at -1 evaluated on both these functions. So when that happens, you just put a solid dot because the closed dot is over top the open dot. Okay? Alright, now we also can do these functions with quadratics. So quadratics a little bit trickier, but not too bad, because we're going to graph them the same way. So go ahead and plot your point on your first function, so -3x plus 5, y-intercept of 5. Then I'm going to go down 3 every time I go over 1. Down 3 over 1. Drawing my little graph. Okay. Next, it only is evaluated when x is less than 1. So 1 is right here. So everything to the left of 1. So it's not going to be right there. And it does say less than, not equal to, so that's going to be an open dot. Now x squared starts right there, but we go up 1. So it's going to start right here, and x squared is going to look something like this. Now, this is evaluated when x is greater than or equal to 1. So starting right here, we have the function x squared. So it looks something like that. And the left side here doesn't exist. So notice, if I plug in 1 for both of these functions, if I plug in 1 from the bottom, I'm going to get out 2. If I plug in 1 for the top, I'm going to get out 2. They're the same y value. So the same thing occurs as it did below here. You're going to have a closed dot at that location because the closed one covered up the open one from the top function. So it looks like a weird V shape, that one does. Now I'd like you to go ahead and try the last one. Alright, this one starts with a quadratic, so x squared starts at the origin. It has a reflection over the x-axis and then a stretch of 2, a vertical stretch of 2, so it's going to look something like this. It's going through the point -1, -2, and 1, -2. You need to make sure you have that. And then this is evaluated when x is less than 0, so everything to the left. So that means going to get rid of all this part. And there is no equal sign, so it's an open dot right there. And now we have the second function, y-intercept of 2, and we're going up 1 every time we go over 2, up 1 over 2, up 1 over 2, and a function like that. This is evaluated when x is greater than or equal to 0, so it does work at 0, so I put in a fill dot and I go to the right, and everything to the left does not exist. So our graph has this jump with a hole on the x negative 2x squared part of the piecewise and a closed dot on the 1/2 x plus 2 part of the piecewise function. Alright, so that is all we have for piecewise functions. You just have to make sure that when you're evaluating a piecewise function, you have to make sure you are putting it into the correct part of it. And when you're graphing a piecewise function, graph each part separately and erase the parts that are restricted by the domains, restricted by these x conditions. Otherwise, that's all we have for piecewise functions.